right, we had started section 6.4, proportional reasoning, last time, and I believe we had gotten just to the very point where we defined what a proportion was, and we said that a proportion is simply a statement that two ratios are equal. Does that sound like where we left off? Okay. So what we're going to do next is we're going to talk about some proportionality theorems, and then we're going to give some examples and do some work with proportions. All right, so proportionality theorems. Theorem 620 is one that you know and love and have used so many times that you have a special compassionate name for it. Theorem 620 says that if A over B is equal to C over D, that is a proportion, that this will be true if and only if A times D equals B times C. And what name have you given this, or somebody given it, that you call it all the time? What do you call this? Cross multiplication. You guys know that, right? I will sometimes have students draw this picture here. And then occasionally I've had a couple people identify this. This is a butterfly. So whatever picture image in your mind works for you, works for me. A times D is equal to C times B. Okay. Theorem 621 says for any rational numbers A over B and C over D, you can't have denominators of 0. We had that issue on 620. This one, however, says my numerators are not going to be 0 either, right? A and C are not 0. That A over B is equal to C over D, if and only if B over A is equal to D over C. What happened to get from the first proportion to the second one? They flipped them, and they flipped them both, right? So if you take two fractions that are equal and you flip them upside down, they're still equal. That should make sense to us, right? And you just flipped them both upside down, of course they're going to be the same. Okay? And if you're wanting further sort of justification, you can take a look. The diagonals are still the same, aren't they? Same diagonal you had as before. It's another further justification that it really is okay, does work. All right, 622 says, again, A over B is equal to C over D. We've got some conditions on what can and can't be 0. Pretty much we're just not going to have 0 in our values here, okay? That this will work if and only if A over C is equal to B over D. What changed from the first proportion to the second proportion? They switched the C and the B. They switched those two, right? They were here, B on bottom, C on top. Now B is on top and C is on bottom. This feels like a funny switch. You'll actually see that when we do our examples that this happens all the time in our examples, where we're going to do the problem in different ways. So maybe Caitlin and Jamie do the problem. They both get the same answer, but they did it in a way, they set it up in a very different way. And usually the different way they set it up has to do with this particular switch right here. That's usually the way it works. So taking a look at this, if again you're not quite so sure, like, does that really make sense? Take a look. The diagonals still form that same diagonal butterfly cross thing going on. It still cross multiplies to being the same values, right? AD is equal to CB. Now, if I'm able to change B and C's diagonal, do you think I'm able to change A and D along the diagonal? Yeah, as long as I don't have zeros in weird places, I definitely can. So there's nothing special about the BC diagonal here. They're just only writing down one of their two options because the other one's just really the same thing. Okay? All right, we're going to take a look now at solving some proportions. Now, today I will tell you, and I will tell you again, I'll remind you when you get to the test that this will be a true statement. It'll be true on this homework assignment. Every problem in this section needs to be solved with a proportion. That's the point of this section of material. I am fully aware that there are other ways of solving a problem, and most of the time you have freedom to make those choices. But in this section of material, I'm wanting to make sure that you understand this concept of solving. Is everybody good with that? Somebody on some problem is going to do something differently, and you're going to get a right answer, and you're not going to be happy with me because I'm going to take points off because you didn't use proportions. Okay, so whatever it takes when you write this on your test, when you get your test on Thursday, right, use proportions, use proportions. We're not setting up equations, we're using proportions. Okay? All right, Jim found that after working for 9 months, he had 6 days of vacation time. If he accrues vacation time at the same rate, how many days would he earn in 2 years? Our goal when we solve these problems is to try and figure out what things are being compared. So somebody tell me something that's being compared here. Days of
vacation time to the months he works.
Right. The days of vacation time to the months that he works. Is everybody with me? Okay. So you have options. You can either decide that the left-hand side of your equation is the days. You can decide that the right-hand side of the proportion is days. You can decide that the top of your proportion is days or the bottom of your proportion is days. There are 4 distinctly different proportions that we can set up on this problem that would all be correct. We just decide where we want to put the days. So you guys tell me, where do you want to put the days?
On the bottom.
On the left, on the bottom. I heard 2 things. I heard the left one first, I think, from Leah, so we'll go on the left. So days are going to be on the left. So if days are on the left, what's going to be on the right? Yeah, the months, right? Or months or years or whatever. It's the time working. So we either have to do it in months or in years. All right, so days of vacation is what's on the left. So one of the days of vacation that he has right now is he has 6 days of vacation. This is like right now. So the other thing we're comparing here is now versus later. Are you guys with me on that? What's going on now versus what's going to happen later. And the later number of vacations is exactly what we don't know. So we're going to let that be our variable, and you can choose your favorite variable you want. Okay, it doesn't matter. X is probably what all of you are going to choose, but you don't have to choose X. Months. How many months has he worked now? 9. How many months will he have worked later? 24. And then what are we going to do to solve this proportion? Cross multiply. That was theorem 620, 21. I can't remember what the number was. What was it? 620. All right, so now I have 6 times 24. What's 6 times 24? What was it? 144. Sorry, I couldn't hear that very well. And then 9 times x is 9x. Then what will we do? Divide by 9. X will equal 16, and it's 16. Oh, good. Vacation days. At least the days has to be on there. Vacation days would be even better. But you do need to label what it is that you found. 16 is not a sufficient answer. Okay, does that make sense? The more labeling, the easier it is to keep track of what you've got going on. On a city map, a rectangular park has a length of 4 inches. If the actual length and width of the park are 500 feet and 300 feet respectively, how wide is the park on the map? So somebody tell me something that's being compared.
The length.
The length and the width then, right? Okay, so where do we want to put the length? Top, bottom, left, or right?
Top.
Top? All right, we'll do top this time. Length on the top. The width would be on bottom. Now compare with me left versus right. What's the other comparison that's being made? Like last time it was now versus later, right? That was another comparison. It's like the map length or whatever, the map values and the real life values, right? So the values on the map, which we said are in inches, compared to the values in real life, which are in feet. Okay, so what is the length on the map in inches? 4 inches. And I tend to not put units as I'm working through this, and I do my units at the end because it just is a little bit messier to deal with them in the middle of it. What's the width in inches? That's the thing we don't know. Okay, so we're going to let that be x. What is the life, the number of feet in length in real life? How much was it? 500? And what's the width in real life? I said I wasn't going to do the feet, and then I just did it. Let me try that again. It was 300? And we're going to cross multiply, right? Right? So 4 times 300 is what? 1,200. And then 500 times x is 500x. And then what would I do? Good. All right, 1,200 divided by 500 is what? 2.4, and I even like you said inches. Good, you got the units on there.
Wait, how we get 2.4?
We divide 1,200 by 500.
Oh.
This one right here. Any other questions on that one? Okay. So it's a little bit of a variation of what we've been doing. Kiera and Dora worked 3.5 and 4.5 hours respectively on a programming project. They were paid $176 total for the project. Because Dora has fairness as one of her strengths, she wants to make sure that each of them are paid according to the time they spent. How much should each of them earn? So splitting it in half wouldn't make sense. Why? It didn't work the same amount of time. Okay? There's at least two distinctly different ways to set up this problem. So I'm going to ask you what the comparisons are. We'll do it one way, and then I'll show you another option in case anyone else thought of it differently, or even if you didn't, so you can see another way to do it. What comparisons are being made? Money and time. Okay, so somebody tell me where you want to put the money. On the bottom. Okay, so we've got money on bottom. And so if we're going to do money on bottom, then we're going to do time on top. What other comparison is made?
How much Kira and Dora worked?
Yeah, the individual girls' salaries and money, right? Okay, so we had Kiera on one side, so I'll put her on the left, and Dora on the right, because that's the way they were introduced to us in the problem. This is the normal way people tend to set this problem up, and I'm not sure that it actually is the cleanest in terms of solving it, but it's the most natural in terms of reading it. So, how much time did Kiera spend? Okay, and I'm going to put it as a decimal. You guys good with that for now? Okay. How much time did Dora spend? 4.5. How much money does Kiera make? We don't know, so we're going to put X. How much money does Dora make? We don't know. But we can't put X because that would mean it's the same amount, right? So that's not right. So what should we do? But then I have two variables.
The total minus
Say that very loudly for me.
176 minus X.
176 minus X. So no matter how much Kiera made, Dora made the rest of it, right? So this avoids having to have a second variable in the problem because there really is a relationship between them. They have to add up to 176. Okay, so now when we cross multiply, this is why this one's not as easy to solve as what I'm going to show you in just a second. When we cross multiply this diagonal in red right here, we have to distribute the 3.5 to the 176 and the X. So just as a reminder to do that, I'm going to write it out one time. So this is supposed to be 3.5 times 176 minus X. And then the other side of the diagonal is the other diagonal is 4.5X. So we have to remember to distribute this if we do it this way. So what is 3.5 times 176? And then it's minus 3.5X, and then equals 4.5. All right, now what? Add my 3.5x. So I have 616 on the left. These both have x's on them, sorry. I left those off. And then I have, I think somebody already told me 8x on the right. Then what? Divide by 8. What will x equal? 77. So now let's make sure we're answering the question asked. We solved the proportion we set up, but the question says how much should each one earn?
So that would be Kiera gets 77.
So Kiera has 77,
Dora gets 99.
and then Dora has what's left, which would be 176 minus that, or 99. Okay, does that make sense? Okay, let me show you the other comparison that you could make. The other comparison you can make has to do with not comparing Kiera to Dora. Still comparing time and money. Okay, so the time and money, I'll leave it where they are, time on top, money on bottom. But instead of comparing Kiera to Dora, I'm going to compare Kiera, and again, I could use Kiera or Dora, it doesn't matter, but I'm going to use Kiera compared to the total amount. Okay, so Kiera worked 3.5 hours. Kiera made X dollars. That's the same. The other side, however, is the total amount worked and the total amount of money made. How many hours total were worked? 8. How much money total was made? 176. It simplifies the setup a little bit to think about it this way. We still end up with the same cross multiplication. So 3.5 times 176, that's still 616. X times 8 is still 8x. And we still end up with the same $77. But you're thinking about the comparison a little bit differently. Both of them work. There's nothing right or wrong about either one of them. They're just different. Okay? At Rattlesnake School, the teacher-student ratio is 1 to 30. If the school has 1,200 students, how many additional teachers must be hired to reduce the ratio to 1 to 25? Okay? This is not a straightforward problem like the last ones have been. There's more involved in this one. So what are the things that we're comparing here? Students to teachers. And what else are we comparing?
Now and then.
Well, that's going to be actually a second question, Hannah. So we're going to have to do the now and then afterwards. Let's just do the now for now. What else did you think?
Just the two ratios, you gotta figure out how you can lower your first ratio at 1 to 25, 1 to 2.
Again, that's going to be coming about by doing the problem, the second part of the problem. So let's ignore the 1 over 25 at the end for the moment. Just thinking about the 1 to 30.
I want to find out how many teachers there are.
You got it, Madison. We need to figure out how many teachers there are, right? Because so far in this problem, it does not tell me how many teachers I have. And in order to figure out how many I'm going to have to hire, I need to know how many I already have. You guys with me? So really, what our comparison is, it's teachers to students, but it's the ratio of the teachers and students compared to the actual number of teachers and students. Okay? So we have, again, I'll just set this one up. So we've got our ratio on the left and our real life number or real values, the actual number on the right. And then we'll do teachers on top and students on bottom. And if you set it up with a different correspondence, it's still going to be fine. So the ratio is 1 to 30. How many real life teachers do we have? We don't know. How many real life students do we have? 1,200. So if we cross multiply this, we get 1,200 equals 30x. Divide by 30. How many teachers do we currently have? 40 teachers. So this is now. Okay. So this is the part where I was telling you guys before, we want to do a second problem. The second problem is the later problem. What do we want to have happen? I still want the same teachers over students. I still want the ratio compared to the actual people involved. But I just want to figure out what it is I want to have happen, not what I actually have happening. So I want my ratio to be 1 to 25. I may, in fact, want students to be fewer, but I don't have that choice. They're still there. Okay, same 1,200 students. That doesn't change. But what I don't know is I don't know the number of teachers. And you know what? Let me use a different letter because I don't want you to think that it is the same X. It's not meaning the same thing. So I'll use Y. So now I have 1,200 equals 25y when I cross multiply. And then if I divide by 25, what do I get? 48 teachers. And this is what I want. Right? Now go back to the question. What did it actually ask me for? So how many do I need to hire? I need to hire 8. Does that make sense? All right, we're going to detect an error next. Mary is working with measurements and writes up the following proportion. 12 inches over 1 foot equals 5 feet over 60 inches. How would you help her?
You have to have the same, like, not denomination, but the same measurement on the same line.
Okay.
So it's like if she can't have inches on the top and inches on the bottom, like across from it. She has to have inches on the top and feet on the bottom.
Okay, so if she's comparing inches and feet, they need to be in the same location. The inches need to be in the same spot. Okay? What if you just looked at the left-hand side by itself? Is that ratio correct? 12 inches and 1 foot? Yeah, it's the same value, right? 12 inches is the same as 1 foot. What about the ratio on the right, 5 feet and 60 inches? Yeah, so she has the right ratios. She just needs to switch one of them, invert it. She needs to flip one of them to actually have the proportion set up correctly, right? Okay, so let's write down a couple of things. So her individual ratios are right. It's a good idea to tell students what they do have right, because if you tell them they're wrong and they are not listening after you say wrong, then they don't know what they did wrong. You just told them they were wrong. Do you understand what I'm saying? The individual ratios, the left-hand side is correct, the right-hand side is correct. It's the comparison that's wrong, right? The comparison is the actual proportion. So we'll go back to what Hannah was saying. So something like she needs to have, and I heard someone else use the word unit. I like that word. Needs to have the same unit in the same location. We'll say corresponding location. We even say same units in corresponding locations. And then maybe an example. How could I change this so that it would work and it would look right? There's more than one option. So what might you change?
12 inches over 1 feet equals 60 inches.
So this is one correct option. Not the only option, not the only answer, but it's one possible fix. All right, last question. Amy's friend told her that the ratio of boys to girls in her classroom was 5 to 6. Amy was surprised that her class would have only 11 students. What would you tell her?
That doesn't mean that's how many people are in the classroom. That's like for every 5 boys you have, there'd be 6 girls.
So 5 to 6 means for every, what do we do first, boys? For every 5 boys, there are 6 girls. could it be that she only has 11 students? Would that actually be a possibility with the information given? Yeah. So she could have 11. Or what else maybe? 22. What else maybe? 33. And we could continue adding basically 11 to this every time, right? Probably past 33, and you would be a struggling teacher. I know I would. Yeah, so it's the ratio. I think you described that very well, Leah. It's this issue of how many to something else, right? How many boys to how many girls, and so we can have multiple groupings of 5 boys and 6 girls within the classroom to still make up the whole classroom as a whole. All right.